Okay, Assalamu alaikum. So today we are going to discuss the pipelines in data paths and what is the concept of pipelines. So this module will be divided into three sections, which are pipelines. Then we are going to discuss part 1 for reduced instruction set computer and part 2 for reduced instruction set computer. So to understand the concept of the pipeline, let's take this pipeline as an example. In this pipeline, you can see that the total time needed is to complete one instruction is 0.6 to read from the register file, 0.2 to pass through the multiplexer, nanoseconds of course, 0.8 nanoseconds to finish the function unit, and then 0.2 once more to finish the mux-d, and finally 0.6 seconds once more to write back the instruction. Now, if we sum all of these times, 0.6 plus 0.6 plus 0.2 is 1.4 plus 0.8 is 2.2 plus 2.2 is 2.4 nanoseconds. 2.4 nanoseconds. This will give us 1 over 2.4 nanoseconds is our frequency for our processor. So if we are able to reduce this number, then we will be having higher frequency. So in order to do that, we try to pipeline our data path. So this is our concept over here. So the maximum delay values for each component is in a typical data path. So the maximum of 0.8 nanoseconds is required for the two operands to be done. So over here you can see that our conventional data path will have 2.4 nanosecond, whereas our pipelined data path we have this configuration. In this configuration we divide the cycle into smaller cycles, as you can see here. This cycle is called operand fetch, this one is called execute, and this one is called write back. In operand fetch, what do we need? We need 0.6 plus 0.2. In execute, what do we need? 0.2 plus 0.8. In write back, what do we need? 0.2 plus 0.2 plus 0.6. So the maximum time needed basically is 1 nanosecond, and this 1 nanosecond will give us a total frequency of 1 gigahertz. Now the 2.4 nanoseconds, which is for the conventional data path, will in turn give us around 416 megahertz, whereas the 1 nanosecond will give us 1 gigahertz, which is a huge improvement. So delay paths that pass through both the data path and the control unit limit the frequency for even smaller values. For the data path alone, and for the combination of the data path and control unit single cycle computer, the execution of micro instructions constitute of the execution of an instruction. So we add all the micro instructions together to get one instruction. Thus the rate of the execution of the instruction is equal to the clock frequency. Now suppose that the data path rate is not adequate for a particular application, meaning that the data path frequency is too low and we want faster frequency, and that there are no faster components available which will reduce the frequency below 2.8 nanoseconds required to complete the micro instruction. So still it may be possible to reduce the frequency, thus by breaking up the 2.8 nanosecond delay path into smaller cycles, which are these cycles over here. So you can see here that we have the 0.6 plus 0.6 plus 0.2 plus 0.8 plus 0.2, which is equal to 2.4 nanoseconds, which in turn give us a frequency of 416.7 megahertz. Whereas for the pipeline, the maximum time you saw here is 0.8, and here is 1, here and here is 1. So the maximum frequency is 1 nanosecond. 1 over 1 nanosecond is 1 gigahertz. So we find that it's quite a good improvement compared to that. So we need, in order to do this, we need 3 sets of registers, and these registers are as follows. We need this part, the hashed part, which is part of the register file, and these platform registers, and this platform registers. In order to move from one cycle to another, because this will be in cycle number 1, this will be in cycle number 2, and these will be in cycle number 3. In order to move from one cycle to another, we need platform registers. These platform registers will basically do what? Will hold the data in the intermediate stages. So 3 sets of registers are used to break down the original data path. The register file contains the first set of registers. The cross-hashed covers the top half of the register file, since the lower half is viewed as a combinational circuit. The 2 registers are used to store data A and mux B, which is these 2 registers. This is data A, and this is the mux B part. And the third one is used to hold the function unit, which was going to feed the mux D input. So this the process of an instruction in a pipeline consists of at least 1 plus n. So in a pipeline, you cannot say that I have a single cycle instruction. There is no such thing as a single cycle instruction. We have an instruction that will be executed with at least n plus 1, n greater than 1 steps. Then how do we achieve the single cycle computer? This is what we are going to talk about later on. So the length of the time required to process an instruction is called the time latency. Based on the analogy of pipeline data path with n stages, where n here we have 3 stages, so n may be 3, 4, 5, 6, anything greater than 1, and non-pipeline paths, the former has processing rate throughput for instruction that is n times the later. So the pipeline is n times faster than the normal data path. So if I have a data path, a conventional data path, and I have a pipeline which is 5 stages, the 5 stages pipeline will be 5 times faster in theory. 5 times faster in theory. So the desired structure is based on the non-pipeline data path, is shown in figure 5.1b, which is this figure here. Okay, this is the pipeline. So the operand fetch is a stage 1, the execute is a stage 2, and the write back is stage 3. These stages are labeled at the boundaries at their appropriate abbreviations. So if you see here, I can highlight them. Here are the stages. Here we have the operand fetch, here we have the execute, and this is the write back. The write back is basically the register file. This part should be down here, but to make things clear, we kept it up and we kept one register file. So the data within the pipeline moves synchronously with a clock at which controls the movement of each stage from stage to stage. This has some interesting implications. First of all, the movement of the data through the pipeline is discrete steps rather than continuous, because we have on a clock. So all the data is moving through the clock, so everything is moving discrete. The length of the time each stage must be the clock period of the same for all stages. Since we have only one clock for a computer, then the length for all stages should be the same for all, and it is the longest within the pipeline. So to provide the mechanism separating the stages in the pipeline, registers are placed between these stages. Now, in figure B, stage 1 of the pipeline has a delay of 0.6 plus 0.2, which is, I will go back here. We are talking about stage 1 here. You see here we have 0.6 plus 0.2. 0.6 to read from the register file, 0.2 to pass through the multiplexer. Passing through components will delay your signals. Okay, keep in mind, passing through the components will always delay your signals. Now, the second stage will have a 0.2 delay from the platform, 0.8 from the function unit. So we have from the function unit we have 0.8 nanoseconds, and from the platform we have 0.2 nanoseconds. So this gives us a 1 nanosecond. This gives us a 0.8 nanoseconds. Okay. And the final stage, as you can see, stage 3 has 0.2 delay from the platform and 0.6 to write to the register file. So this delay will give us 0.2 plus 0.2 plus 0.6. So here we have 0.2 from the platform, 0.2 from MUXD, and 0.6 from the register file. So this will give us also 1 nanosecond. So in total, we will have a maximum frequency of 1 gigahertz and a clock frequency of 2.4 a time delay of 1 nanosecond. Now compare the 1 gigahertz with 416 megahertz, we will get a 2.4 times speed. Now in theory, what we said over here, we should have n times. So instead of having 3 gigahertz, we should have at least instead of having 2.4 times, we should have 3 times. But what happens is we lose some of the parts over here. You see here we have it's 0.8, this is 1, and this is 1. So this one had an extra 0.2 nanoseconds which were wasted. So this mainly will cause these problems. So even though there are 3 stages, the improvement factor has not been 3. The addition of the delay contributes to the pipeline. So we added the delay from the platform registers. So what we added here is 2 platform registers. So here is 0.2 and here is 0.2, and we lost here 0.2. So 0.2 plus 0.2 plus 0.2 is 0.6. This 0.6 basically ended up with giving us that delay. The difference between the delay for the logic assigned, which we talked about earlier. So a detailed diagram of the pipeline appears in this figure, and you can see how things are going. We have here is data A, okay, data A. Here is data B. Here is the function unit. Here is data N. And this is the register file. Now the register file, we have done it here, and it's also over here, but to make things easier, we have done 2 register files instead of having the line. So now you can see the full pipeline in full details. So the first stage is the operand fetch, the second stage is the execute, and the third stage is the write back stage. So this is basically what is said over here. Now executing micro operations, as you can see in over here, if we have instructions, okay, if we have these instructions and we want to execute them, so the instruction, regardless of what is the instruction, will need 3 cycles, which are operand fetch, execute, and write back. So in the first cycle we operand fetch, in the second cycle we execute, in the third cycle we write back. Now instruction number 2, in the second cycle we operand fetch, in the third cycle we execute, in the fourth cycle we write back, and so on. Few things to note here, that the pipeline is fully utilized in this blue area. What do you mean by fully utilized? Meaning in cycle number 3 we write back, we execute, and we operand fetch. Same in cycle 4, 5, and 6. So over here we can say that we have 1 instruction per cycle, because in the same cycle we operand fetch, execute, and write back. Yes, we operand fetch instruction 3, we execute instruction 2, we write back instruction 1, but at this time the pipeline is fully utilized and we have the full pipeline for us. This is the execution diagram. This is called the execution diagram, and you should be able to know how to do it. So over here we have the calculations involved and how to find the execution time for the pipeline. Is quite straightforward and we can find the numbers very easily. Okay, so pipeline control, we'll be talking about this part in the second part of our class. Thank you for watching.